And we'll turn it over to our guest speaker in a few minutes. But first, I want to welcome everyone. My name's Wayne Welk, and ISA New Orleans Section President at the moment. So I appreciate everybody joining us today and our April technical seminar. And we don't have it published yet, but we do have a topic lined up for May. I'm sorry. We do have a topic lined up for May, and so I'll put that out here hopefully later today or tomorrow on our website and all the social platforms. But the topic will be enterprise mobility solutions for industrial facilities, and that's going to be on Tuesday, May 10th, 2022. We had to switch to Wednesday for today for our guest speaker. But typically we're on Tuesdays, so we'll go back to that date. And for the location, there's a good chance we have to kind of make sure where everything's good, but there's a good chance that we can return to in-person in May. We'll still continue to offer the online, just like we did before the pandemic, for those who can't make it to the live sessions, but hopefully we can return to in-person in May. Also want to thank Ronnie Leday, Ms. Bimbo, who's our program manager, for helping get all of these topics scheduled. He's done a great job of lining up our speakers for us so far this year. One other thing I want to comment is thanks to Dean Bickerton, who helped support me last week. We did a STEM fair that was sponsored by Chevron and the New Orleans Saints and Pelicans, and we did it under the name of ISA. So we thought ISA it was better representation for ISA to promote engineering as a career at the STEM fair. And we had a little setup on smart manufacturing and the digital twin and augmented reality. So I posted a few pictures of that setup on our LinkedIn and Facebook and Twitter. So take a look at that. It was kind of cool having our little digital twin running there. And with that, that's about all I have to say as far as things going on with the section. But I want to introduce our guest speaker today, Mr. Jim Key, with the Southern Company Services out of Birmingham, right, Jim, I believe?
That's correct.
All right, I'll let Jim introduce himself, and his title of his presentation is actually right there on the screen, so I will not try to restate it. And with that, I'll let Jim take it over from here. Oh, and just please, stay muted. And if you need to ask a question or want to ask a question, you're free to unmute, or Jim can address that. You're free to unmute and ask a question, or put it in the chat, and we'll monitor that as well. All right, thanks.
Okay, well, New Orleans section, thanks for having me. I think I should first start out by thanking all of you for the honor allowing me to present today. I'd like to get a feel for the audience with a show of hands on some of your background. So if does anybody have any process tuning experience? Just wave your hand. Commissioning, startup, valve selection, optimization. And I saw maybe a hand somewhere there. Well, good. Well, thank you, because you can help me catch any errors during the presentation. And let me talk to you a little bit about myself. Okay, my name is Jimmy Key. I'm a professional engineer in Texas, Nevada, Minnesota, Iowa, and Alabama. I work as a senior I&C engineer for Southern Company here in Birmingham. And my current job is lead for the winterization, the I&C part of the winterization program for the fleet. In the detailed design. Let me tell you a little bit about this presentation. Our Birmingham section needed a technical presentation for a month, and they had trouble finding a speaker, so I volunteered to come up with something. And so I went back, and dusted off a lot of the papers I had. And but between 1987 and 2010, my job was to configure and program DCS systems. First, it was the Honeywell TC 3000 for about 15 years, and then the Foxborough IA for about 7. Around 2010, I went in the nuclear side of things for a while, and they used all analog. So the programming was put on the shelf for a long time. But I did keep my notes and remember some things from back, in the day. So, during that time, I did a lot of control configuration, startup and tuning of all types of equipment, boilers, pulp and paper plants, paper machines, chemical and plastic plants, ammonia plants, and a few others. And, of course, what I found, when tuning, it was important to understand not only the dynamics of the process, but also the nature of the final control device. So this presentation reflects some of my learning during that time. The title indicates a method that may improve control by modifying the output of a controller to make a control valve exhibit a more linear flow characteristic. Here we have the agenda, and I'll try to go through it in less than an hour. I'll start from some of the basics and work our way to the examples. Let's see. Well, the basics. Let's talk about the basics. The basic review is what is linear and nonlinear. Okay. So linear is basically a straight line. It's really, and nonlinear is any equation that is not to the first power. So you see below, it's got a square and it shows it's nonlinear. A little about the control variables we deal with the most often. All these variables are linear with respect to flow. As you can see, the differential of volume is flow times time, fixed density, and level has all of those attributes, making it linear with respect to flow. Level, pressure. I use this example, a temperature example, temperature water flow calculation example, really substituting enthalpy for temperature to show that it's a linear process. There's no radicals, no powers in here. And I just use this other example. Temperature is linear with respect to mass flow in this mass energy transfer equation. Any questions so far? Okay, this next part is going to be kind of like pulling teeth, but we'll go through this as we go through the fixed speed centrifugal pumps. Okay, this is a diagram of a fixed speed centrifugal pump, in a control loop. You got minimum flow valve, you got your control valve, your level control valve. And in this system, let's just look real quickly at each component of this equation, which really defines the drops across the system. We got our net positive suction head into our pump. That's a positive. We've got our pump, which is positive. We got drops caused by our valve and the velocity of the fluid through the piping. We got losses due to elevation and to back pressure. You add all that up, it should come up to 0. Now, looking at the pump itself, the head that it generates follows the curve, from higher, where it has higher head at lower flows and lower head at higher flows. And you can see it's nonlinear. So this is what you see in the manuals. And this will take care, that's probably your minimum flow for that pump that you want to make sure that you have. And of course you do that because you don't want to overheat the pump and cause cavitation and flashing inside the pump. Pipe losses due to velocity is nonlinear, as you can see in this equation. Elevation changes are basically constant. And the DP loss across the valve is nonlinear with respect to flow. As you can see, here's the DP, and if you rearrange this equation, it's nonlinear. Okay. Now, the reason I'm talking about linear and nonlinear is to see that there can be a balance that can be made with the control valve, with its inherent flow characteristics that actually produce an installed linear flow. So, but real quickly, where does our data come from when we do these, the sizing of this? The data usually comes from what we call a pump run, and it's done by the mechanical people, and it gives us all the data that we need. Really, they do it to size the pump, and then they allow us a certain amount of drop across the valve, and that's how we end up sizing the valve. This is the ISA liquid flow equation for a valve. It's of course it's nonlinear due to the term in the denominator, and but note that if the DP is constant down below, that the term in the denominators becomes a constant, and this is what you get. That's a linear equation. Nonlinear, linear. All right, so there's two different characteristics we're going to talk about here. One is the inherent flow characteristics, and that's the characteristics when a valve is operating at a constant pressure drop. And then we have an installed flow characteristics, and that's when the valve and the piping effects are taken into account. There are various different types of trims you can get for valves. In most cases, you have in flow, most cases we use equal percentage or modified parabola when we're doing have systems like where we have variable differential pressure across the valve, and we use linear where the pressure is constant. Okay, let's see, this is 16. Okay, so if we recall this, the centrifugal pump system here, we see that the head for the pump, drops off as flow increases, and we see that the velocity due to the pipe increases. Now this is a 100-foot section of pipe, but as it goes up, it becomes more and more a factor. And the available DP for the valve ends up looking something like this, where it starts off high, and then as the flow goes, the available DP is so that's a nonlinear DP availability curve. Okay, so this is right out of the catalog 10 manual. This shows you the for an equal percentage 4-inch V150 the curve, the inherent curve for that valve. Okay, so but if you look to the right, you'll see that because of the head is reducing, the available head across the valve reducing, and the corresponding CV increasing at really at a greater rate, but still a nonlinear decrease when the two the result is be that this equation, these two here end up so that you get a linear flow through the valve. But so, I mean, this is perfect. This is what you want. And the reason you want that, we'll go through that in a little bit, but it's because your PID controller, it's really linear equations. So if you got a linear final element that produces this, then your PID controller will be able to control better. Okay. But if you remember this curve here, this is, this was perfect, for example, that we had. Okay, but not all curves, not all valves have the same type of curve. All equal percentage curves are not the same, is the bottom line there. So they won't produce the, a linear result is perfect as what an ideal curve would produce. And these differences result in a nonlinear process gain as you go through the stroke of the valve. All right. if the wrong trim is selected in the application, then the installed flow characteristics can be troublesome. You know, like this is an example where a linear trim was put in on a application where you had, you know, variable DP, where you should have an equal percentage, and this is the installed flow curve. This was the inherent, but this is what you end up getting. Let's see. If you use a quick opening valve that has quick opening characteristics, which is usually valves like butterfly valves, things like that, then your actual installed and your inherent characteristics are basically the same. And because you got a, you know, quick opening, it goes up to close to 100%. Right at cracking the valve. This valve is not good to use for any type of control. People do it, but it's not good to use those. In most cases, there will be some difference between the valve's ideal and actual flow characteristics. But re-characterization of the control output to move the installed flow characteristics to more linear can help you with stability and minimize valve travel. All right, now, does anybody have any questions on material before that? Okay. Again, what we're trying to do is trying to show is that by having a more linear flow characteristics from your valve, that your PID controller will end up with better control. You'll be able to tune it with probably more gain and less integral. And the result should be that your integrated sum of errors will decrease and your valve travel should decrease. Now, this isn't used for, I would suggest that only use this where you have some problems, like, you know, if the valve is hunting or things like that, because if you know, you make a step change here, the valve may overshoot some, and then up here, if you make the same step, it may not get there. Can I open it up? Let me see chat. I see a chat. Okay. Anybody got any questions so far? Okay. All right. All right. So let's go on to, that's where what we looked at before were instances where the DP across the valve varied, and you know, it varied due to the pump, you know, running out on its curve, and due to the velocity causing loss of DP in the piping system. All right, so constant DP, well, you know, how do you get it there? Well, sorry about that. Well, you can have a variable speed pump to control the pressure. You can have pressure control You can maintain a feed tank level control, gives you a constant head pressure. You can have pressure headers, like steam headers or back pressure regulators that will maintain a constant DP across the valve. And there are probably other methods too. Well, and so with a constant DP system, installed valve characteristics they follow their inherent CV curve more closely. So whatever you get off the shelf, if it's a constant DP, it will follow that curve. So you want to use a linear flow trim in that case. You remember, this is what we get when we have a constant DP across the valve. And this is a diagram. This is a variable speed pump. And as you can see, that as the pump speed increases, not only do you get more flow, but your head increases. And what happens to your valve, if it's a linear valve, the gain will shift. So this is a good application to use an adaptive gain to correct it. Because you want it to be linear the whole time, and you want the gain to be to have a linear profile. You don't want it to diverge. All right. So when would you want to use recharacterization? Well, one is when the valve inherent curve is nonlinear and the DP is constant, and you don't want to change the trim, or you can't because of the size of the valve. When the valve's inherent curve is linear and the DP varies across the range, you want to, instead of changing it to a equal percentage trim, you might want to limp through and change it. Or in some cases, when a valve needs to have some sort of breakthrough, like when it opens, I saw this in the temperator, where at the low levels, the steam going through the valve, the water flow was so low that it would flash, in the steam line, and you couldn't get water into the steam line. So sometimes you have to take a step up, like going from 0 just to 5% open, just to start seeing some sort of effect and overcome the flashing. That's just one example. And why would you want to recharacterize? Well, many high flow valves or ball valves design with nonlinear flow characteristics that don't match the ideal curve. And we saw that back in the previous slide. Sorry, was that the previous slide showing all those other type of valves and how their inherent flow characteristics differ from each other. You want to recharacterize because the PID is a set of linear equations, with respect to error, time. And by doing that, you may reduce your interval term and allow your proportional term to do more work. And you'd have less overshoot and less integral needed to reach the set point. Now we talked about, the two different, the variable DP and the constant DP, why we may want to do recharacterization. Now, I just want to step through of, how you may want to do it. Of course, if you're offline, you can, you can go, if you have flow data and valve data, this is good, but you have to check to make sure that the conditions are stable, when you choose the data. And then you just interpolate the percent at fixed linear flow intervals, and then you build your XY table for the controller. And of course, at the end, you want to test it by opening it from 10% from your controller, which will go through your characterization block, and you should see at those intervals, you should see 10% flow. And so if I go, so say the maximum flow is 100, I open it 10%, I should have a flow of 10, and so forth. At 90, it should be 90. 100, it should be 100%. If you're online, you can open the valve. I think I used, I said 10 at one time, but I think I used 5% intervals and measured the flow, and then I interpolated percent open at 5% flow intervals. And then I built the XY table for the controller, and then I tested it. Now, one thing that you have to be, when you do this, in the DCS, when the operator goes in manual and they change the valve from 10 to 50%, okay, you want the valve to go 50% open, no matter what. Okay, when he says go to 30%, he puts it in there. In manual, he wants to go 30%. Well, this is the construct of the algorithm. We've got our control variable coming in to our controller, and that output of the controller, again, it's 0 to 100%, and it's linear with the error, and it goes to our characterization block, to a transfer, and this is an auto, and that goes to the valve. Okay. When in manual, you have to initialize the controller, and you see how on this block we got our XY. Okay. Well, you have to flip it so that in this block it's YX, out and in. Over here it's in and out. And what that will do is, when the controller will come back over here, and when they go back online, go back to automatic, you won't see any bump. This is for bumpless transfer. Now, there's been some arguments against re-characterization. Arguments have been, it's got to be maintained. Can be variable for different conditions. Well, so can any type of tuning. And they say it can confuse the operators, but if you go and you construct it like this, then the operator shouldn't be confused, because this is hidden from them anyway. This part, they're just concerned when they go in the manual where that valve needs to go, like when they're doing calibration and things like that. So, you know, you have to pick and choose where you do this, but there are some places that it could be advantageous. They talk about, you know, dampers being in other devices, you know, they're consistent in their non-consistencies and in their non-linearity. That can be an issue. You know, they talk about boiler feed water valves are inconsistent in their non-linearity due to high variable DP across the valve and a variable number of boiler feed water pumps running. Apparently they have found that because of some of the algorithms that we use, you know, today, that the characterization is needed, because they move the variable speed drive on the pump, so it keeps the valve in a linear position. Now, you know, we talked about the marriage between the final device and the controller, and we're going to go through a few of these controllers and just look at them. This is what they call the parallel controller. This is mostly what, you know, they teach in school, so, you know, people can understand it, but it's not. Some people use it, but you know, there's no common gain on all three terms, and so it can be challenging to get this tuned. Let's see. All right, the next one is the interactive. Of course, this was kind of a legacy from the pneumatic era. When you select this type of algorithm, the tuning rules that you use for this, you need to, you know, be sure you use the right ones. And for this interactive, the Ziegler-Nichols rules was developed for this form here. And finally, we got the non-interactive. You know, this is you know, called the ideal standard or ISA form. And, you know, when you're going and you tune in this, you know, there's two forms that you can use, two rules, you know, the Cohen-Kuhn and the lambda. I think most people use the lambda rules, you know, for this form. So as you see, you know, a classical PID consists of a linear structure. So we have, what we're trying to do is get a linear structure married up with a linear flow characteristic of your final device. And the control process reacts faster and has less steady state error when you use a larger gain, as long as the closed loop system remains stable. So let's talk about performance of the, you know, good control loop performance can be summed up, and it's got maybe a few more that, you know, a variable stays within the dead band of the operating set point. The integral sum of errors is small. You want to minimize valve travel. So, you know, this avoids, you know, hunting and wear of the valve. You want to have, when you tune it, you want to have an acceptable trajectory to set point when you introduce a new set point, so you don't overshoot or you never reach steady state. Of course, you want minimum overshoot when moving to a new set point, but you wanted to get there as quick as possible, usually. And you want minimum valve movement when at set point, and that's the hunting where it might be hunting, and you want to make sure that there's stability of the process in the face of disturbances, and that usually takes when you first tune. That's why you have to go back and look at it again and again, because process non-controlled processes will affect the tuning of your valve. And so this is just a curve. I think that we've all seen this. Tell us water rise time, amount of overshoot, integrator. And so the minimum settling time is virtually equal to the natural period of the process. So this is settling time. Okay, we're doing pretty good on time here. It's got a couple of more. Here's some process examples. This is steam drum level control, using a VFD to keep the CV in a linear portion of the valve. So as you can see, here's the valve output, and as it goes beyond a linear portion of that valve, it will increase or decrease the speed. And this is just another identical slide of showing a variable speed pump and how the gain will change. This is the temporary example when the valve it needed to open more initially to overcome some flow impedance caused by flashing when it first opened. And so that is about it. We can go through the summary. Centrifugal pump curves are nonlinear. Flow velocity in pipes adds another nonlinear component. A 10 foot per second flow velocity in short runs, less than 100 feet. The velocity has a small effect. It's best to get empirical flow data versus percent open before you do the recharacterization. You want to place the recharacterization curve between the controller and the auto manual station. You want to provide initialization to the controller when in manual through the reverse characterization. If the process benefits by recharacterization, then always do the recharacterization before tuning. That's important. Use equal percentage valve inherent characteristics for fixed speed variable DPs, and for where you have long pipe runs greater than 200 or restriction orifices. Linear valve characteristics, constant DP, constant inlet pressure, short runs. The PID control algorithms are linear with error in time, and use the correct tuning method for the chosen algorithm. And the more linear the flow with percent open, the better and quicker control is possible. Higher gains, less interval. Of course, you want to avoid swinging the process. And variable speed pumps shift the head, cause a linear gain change in the valve if in the short pipe runs. And if variable speed pumps that change DP due to load, they should use the adaptive gain tuning for each of the loads. And so, as we know, every case is special. Each is unique in its own way. So you have to use judgment when you're tuning a process. And that is it. And I appreciate everybody joining me today.
Thank you, Jimmy. We got about a couple minutes before the top of the hour, so if anyone has a question, feel free to unmute and ask it live or type it in. Got one in the chat there, Jimmy. I don't know if you can see that. Are there any tools out there for assisting in computation of the installed characteristic, such for greenfield designs?
Yeah, well, there are. I mean, I have. Let me see if I've got that here. I'll show you kind of if I can find it. I may have to. It may be under this. Let's see. Now I'll move this out of the way.
Looks like a good engineer's desktop right there.
Yeah, it's got a lot on it, so, and sometimes it takes me a while to find what I'm looking for. I need to organize a little bit better. Let's see if I got that here. I do have a program that does that, but this is my work computer, and they're very persnickety about putting homemade software on their systems. But if you'd like, you can send me an invitation, and I can get on my home computer and I can show you some software that will do that. Anybody else? So let's see, let me bring this back up. Yeah, I'll yeah. Let's see what I do. Okay. All right. Anybody else got any questions? I mean, so again, this is this knowledge I got from years of doing configuration, tuning, programming, things like that. And and we back in those days we had a little bit more leeway of trying different things, and this seemed to, in some instances, it seemed to help with the hunting that you see your controllers doing in different processes, and due to the non-linearities of the process. And so if you can find a good application, it may work for you. So that's well, I certainly appreciate you guys, having me. It's getting close to the end. Is anybody else got any questions? Anybody else got any? I asked you at the very first, if I was in, if the presentation could be improved a little bit, I'd be more than happy to hear your feedback. I can't do anything about the presenter though.
All right, it's all quiet. Well, if, as always, feel free to, and if you want to reach out to Jimmy personally, we can, I got his email address. You can reach out and share. So last call for any questions or comments. So once again, Jimmy, I appreciate you taking the time to join us today and present. It's always good. I don't think we've had a process type topic in quite some time, so it's good. It's good to have done that. So we appreciate your time.
Okay, well, I appreciate you having me. And
great presentation. Great presentation. Thanks, Jimmy.
Well, thank you. Thank you for that.
All right. Well, and also want to thank everyone for attending, taking time out of your day to join us too. And like we said, we'll have our next session will be May 10th. I'll get the details out on that here very soon. And hopefully we can be back in person. So once again, thank you, and everybody have a great afternoon.
Thank you, everybody. Bye-bye.